Hello, welcome to General Chemistry 2. The purpose of these lectures or videos is to give you a chance to go over again the material that we've covered in class at your own pace. So if you don't understand something in class, you can go back and listen to the appropriate material, or you can see some of the worked out examples done a little bit slower. And again, just gives you an opportunity to revisit any material that you may have missed in lecture. Now, with General Chemistry 2 is, of course, a continuation of General Chemistry 1. And in Chemistry 2, we pick up at Chapter 14 in our book, or our topic is solutions. Right? And solutions is not something that we haven't talked about before. We just haven't really dove into it in very much detail. So let's jump right in and give a little introduction with a lot of vocabulary and some general overview of what we mean when we talk about solutions. So first of all, we're going to remind ourselves that a solution is just another term for a homogeneous mixture, right? So a solution is just what we typically call that type of mixture when we combine two or more substances and they mix homogeneously, meaning they appear and behave as one substance. Now, the reason we spend so much time talking about solutions and dedicated a whole chapter to them, right, is that almost all of the materials that we encounter are actually solutions and not pure substances. To name a few, water, air, coffee, tea, most gas mixtures that we talk about, or most gases that we talk about, are actually really just mixtures in the sense that when we encounter them, we very rarely come across pure materials. Now, in order to understand solutions, we first have to introduce some vocabulary. So, when we think about a solution, it is a mixture, of course, and that mixture has two parts to it. We have what's called the solvent, and this is simply the majority component, or the component that we have the most of. The solute is the minority component or components. So when we're thinking about a solution, we can only have one solvent, but we could potentially have many solutes. So for example, seawater, right, the solvent would be water, and the solute would be any of the materials that are dissolved in there. Sodium chloride being one of them, but also magnesium chloride and other components that are dissolved into the seawater. Now, also I'll remind you that the term aqueous, right, is used when water is the solvent. So when we talk about aqueous solutions, which we have quite throughout the second half of Chem 1, when we use a little AQ in chemical equations, or when we work in lab, we're often working with solutions. Now, if we dive a little further into solutions, what we'll see is that solutions can come where the solvent phase, right, is any of our three basic phases: gas, liquid, or solid, and we can have various solute phases dissolved within those. Now, it's important to note that the solution phase, right, the solution will take on the phase of the solvent. Now, if we have a gas solvent, then really the only type of solute we can have is a gas. So mixtures of gases, as we recall from our chapter on gases, always mix homogeneously. And so, for example, air, right, is an example of a gaseous solution. Now, think about air, right? What would the solvent be? Well, the solvent would be the most populous gas in the air, and that would be nitrogen. Right? And the other gases would be solutes. Now, the most common type of solution is a liquid solution, right? And that's because if we have a liquid as our solvent, right, we can dissolve any of the phases as solutes. So we can have gases dissolved in liquid, example, carbonated water. We can have liquids dissolved in liquids, such as any kind of alcohol beverage, right, which is ethanol dissolved in water. We have, if you think about gasoline, when you put it in your car, typically it has ethanol dissolved in it. So those are all examples of liquid-liquid mixtures. And of course, we're probably most familiar with in sort of our everyday, like with solid liquid solutions, where we dissolve some solid like sugar or salt into water or into some liquid. Now, solid solutions are also possible. Now, we have to talk about this one a little bit more specifically, simply because if we have a solid as our solvent phase, then that means the only type of solute we can have is also a solid. Now, this is where we get all of the things that we talk about as alloys, like brass or bronze, sterling silver, and many other common metal alloys that we work with or that we encounter. And so, but we can't create these solid solutions in the same way that we think about for more common solutions, where we'd simply, for example, take our salt and dissolve it into water, right? We can't mix these as solids. So we can't take two solids and just grind them together. That is not going to give us a homogeneous mixture ever. The only way to create a solid solution, right, is to mix the components in their molten state, or in other words, right, as liquids. So the idea is that you would take your two solids, you would melt them, mix them as though you were mixing a liquid-liquid mixture, mix them so that they're homogeneous as liquids, and then you allow them to cool and re-solidify, and then you will get a homogeneous solid mixture. So we can have all types of mixtures, but clearly the ones that we're going to deal with most commonly are going to be, right, our liquid solutions and some gaseous solutions. Now, when we talk about dissolving things, we have to think about some terms, right? We're going to encounter terms like soluble or insoluble. And all of these are telling us is that something dissolves or doesn't, right? Remember, we had solubility tables where we looked at the solubility of ionic compounds in water. And so all soluble means is that one substance will dissolve in another. And we would say that that solute would be soluble if it dissolves. So sodium chloride is soluble in water. Insoluble is just the opposite, right? It does not dissolve. So oil is insoluble in water. Now, I'll introduce a couple of other terms here. So miscible. So this is a special term that we reserved when we're making liquid-liquid solutions. So this is used to describe two liquids that are what we call mutually soluble in all proportions. And all that means is that when you take the two liquids, you can mix them together, and it doesn't matter how much of each of the liquids you have. So for example, ethanol and water are miscible. And all that means is that we can make a mixture. We can make a mixture, and it doesn't matter how much ethanol, how much water, right? We could have 5% ethanol in water, 95% water. We could have 95% ethanol and 5% water, right? That's miscible. If two liquids are non-mixable, right, we would say they're immiscible, right? They're not soluble in any proportions, like oil and water. So these terms are qualitative, right? They just tell us something does dissolve, something doesn't dissolve, two liquids are miscible or not, right? When we want to start putting numbers to this, getting more quantitative, we use the term solubility. So solubility is defined as the maximum amount of solute that will dissolve in a given amount of solvent. So it's giving you quantitatively how much will dissolve. And so typically, right, there's a limit, right? We can't just continually keep dissolving something in our given amount of solute. So I can take salt and I can dissolve it in water, but eventually I'll reach a point where no more salt will dissolve. I've reached the solubility limit. So for example, for sodium chloride, table salt, right, that's 36 grams of sodium chloride per 100 grams of water at essentially room temperature at 25 degrees. So I can dissolve, if I have 100 grams of water, or about 100 mils of water, right, I can dissolve 36 grams of salt in there, and then if I try to dissolve more, it won't. Now, of course, I can alter that solubility most commonly with temperature and make it either more soluble or less soluble by varying the temperature. And we'll talk about those kinds of things in a little bit later. Now, why does certain things dissolve and certain things not dissolve, right? That's really one of the key points where we want to extend our knowledge. So all the stuff I've talked about up to this point, maybe with the exception of a few vocabulary words, right, is things that we've sort of basically understood as we've gone through chemistry to this point. But when we talk about why something dissolves, there's essentially two reasons that we're going to discuss, or two sort of fundamental reasons that control whether something is soluble or not. The first one of those is what we'll refer to as nature's tendency toward spontaneous mixing, right? When two materials come together, nature's tendency is to have them mix, right? Now, sometimes that doesn't occur, and we'll talk about the reasons that that might be. So we have this tendency, this natural sort of movement toward mixing. And the second idea that we'll talk about goes back to something we talked about in Chem 1, right? And that is the intermolecular forces, right? And you might remember that one of the big things that we talked about was, like dissolves like. This idea that polar materials like to dissolve in other polar materials and vice versa. And we'll revisit that idea. So let's first look at this idea of spontaneous mixing. So if we take, for example, a container and we have a divider there, and on one side of that divider we have, quote, pure water, right? Water that doesn't have anything dissolved in it. And on the other side we have salt water, right? Water that has some amount of sodium chloride dissolved in it. If we remove that barrier, our intuition, right, our knowledge would tell us those two halves are going to come together, and you're going to create salt water that has some uniform concentration where you end up with the salt being distributed throughout the entire container. So this is spontaneous mixing. Now, we see this, this is a sort of contrived experiment, if you will, but we see this at play in nature as well, right? The concept of osmosis, right? Like in our body, right? This was given a little bit of treatment in the beginning of the chapter when we talk about thirsty solutions. This idea that in our body, if you have two solutions of unequal concentration separated by what we call a semi-permeable membrane, right? Now in the body, right, that's going to be our tissue walls, right, which are permeable to certain materials like water and ions. If we have on one side of the semi-permeable tissue, we have salt water of a low concentration, and over here we have more concentrated a sodium chloride solution. The natural tendency toward mixing, right, is that water will flow from the dilute solution. So from what we call low concentration, and when we say that, we mean low concentration of the solute to the solution of higher concentration. And the net result of this is to try to equalize the concentration. So by allowing water to flow from the more dilute concentration to the more concentrated concentration, it dilutes the solution over here, right? So by diluting this, it's trying to bring them closer to equality. So this side losing water will become more concentrated. This side gaining water will become more dilute. And the idea is to try to get a uniform concentration. Now, of course, we don't necessarily get to a uniform concentration in a system like this because things are moving, right? This isn't a stationary system. But this is what happens in the body, right? As materials move through, if we have something of a high concentration of salt that's passing through our intestines, like salt water or just high salt content, right? It's going to pull water from the body, right? This is why it can dehydrate you. So when they talk about drinking salt water can actually dehydrate you, this is why, right? And eating salty foods can sort of dehydrate you as well, right? In a much milder sense. Okay. So this is a real life example of where we see this idea of spontaneous mixing occurring. This idea of going to a uniform concentration. But that really sort of skirts the question, right? It doesn't really answer why the spontaneous mixing occur. Well, one thing that we've focused on throughout the course so far is that many phenomena in chemistry or in the natural world occur because they lead to lower potential energy, right? They lower the energy. They lower the energy of the system. So we think about, exothermic reactions that we've talked about, right? We want to move towards systems where we have lower potential energy at the end versus at the beginning of a reaction. And this is accomplished by releasing energy to the surroundings. Okay, so this is one of the natural driving forces that we encounter is reduction of energy. Now, not every change, right, whether it be physical or chemical change that we see results in a change of energy, right? So for example, when we form a solution, right, we don't always lower the potential energy of the system. Sometimes we do, but not always. So, for example, if I take two gases and mix them together, we have the example here of neon and argon. Now remember, these gases normally don't really interact with each other, right? And so when we mix them, essentially the energetics are unchanged. These gas atoms are still not really interacting with each other, right? There's no increase in attraction. There's no, change that would tend to lower or change the energy of the system. So why do they mix? Why not stay separate? Well, the answer lies in a concept called entropy. Now, at this point, we are just defining entropy. Later on, we'll deal with a chapter on thermochemistry or thermodynamics, right, where we dive much deeper into the idea of entropy. But in sort of this point, entropy is this natural phenomenon where the tendency of energy to disperse, right? So think of this as spontaneous mixing, right? So if I have a system that has constrained energy, so all the energy is isolated in a small volume or a small area, right? The natural tendency is that energy wants to spread out. This is one way to look at this concept of entropy. It's energy dispersal. And so what's happening here is that we have the energy that's involved in our individual systems contained to their individual containers, right? Their boxes. Well, if they mix, the energy that's in, say, this box of neon can now be spread out over both boxes. And at the same time, the energy contained in these set of argon molecules can spread out over the entire box. So now we have this dispersal of energy, right? Spread out over a larger box. So we have a uniform energy sort of everywhere throughout here. And so this increase in entropy of the system is favored. Now, note what I said. So when this energy disperses, when we see dispersal of energy, we call this an increase in entropy. And that is what we're looking for. So systems will tend to move toward higher entropy. So you want to make sure and keep track of that idea. So while we lower energy, right, the movement is toward more entropy, more dispersal. Now, another example that maybe you can think of this a little bit more, well, maybe a little easier because you've experienced it, is thermal flow of thermal energy, right? So if you take a metal bar or a metal, let's say marshmallow roasting stick, right? And you put it in the fire, right? The tip of that gets hot, right? But the heat doesn't stay there, right? That heat, that thermal energy moves up the metal rad. So eventually, even the part that you're holding will get hot, right? If it's, something that allows thermal energy to move through it, like a metal. And so, but in doing that, you're taking that energy that would be confined to the tip, the part that's in the fire, and allowing it to disperse, to spread out over a larger volume, more molecule, more atoms of metal, etc., increasing the entropy. So make sure, key thing here when we're talking about solutions, right, is creating a solution will always increase the entropy. Because for your solute, you're taking the energy in that solute that was confined to the crystals of the solid or the container of liquid, and you're allowing it to disperse throughout the entire solution. So you always increase the entropy when you create a solution. So that's this idea of spontaneous mixing. So let's look at our second idea, and that is intermolecular forces. So we talked about these in great detail in Chapter 12, so I am not going to go through the types of intermolecular forces. If you need to review those, look back at Chapter 12. I've just shown the 4 types here for reference. So remember, we have dispersion forces that are present in all molecules. We have dipole-dipole that are present in polar molecules. We have hydrogen bonds that are present in certain types of polar molecules. And then we have ion dipoles, which are present in a very specific scenario of aqueous solutions of ionic compounds. And so we could ask the questions, right? Is oil soluble in water? And of course, I think we could all answer no. Is oil soluble in something like hexane, right? Mineral cleaners? Yes, right? That's something we can use to clean up oil spills. But why the difference? Now, we've learned this before, so remember, I'll remind you of the idea of like dissolves like. This is what we call a chemist rule of thumb, right? Something that's just something that we can use to, make sort of broad ideas. And so what that means is that when we say like, what we mean is like polarity. Now, another way of thinking about that is like intermolecular forces. So if we tried to dissolve a non-polar material in a polar material, right, they have a mismatch of intermolecular forces, right? The non-polar material can only make dispersion forces, whereas the polar molecule can make either dipole-dipole or potentially hydrogen bonds. And so there's a mix match, right? So if we mix them, the polar molecule is not going to be able to make those nice, stable dipole-dipolar hydrogen bonds with the nonpolar material. And so there's no sort of driving force for it to give up the stronger intermolecular forces that it can make with itself and make weaker intermolecular forces with some nonpolar molecule. And so it just doesn't happen, right? But if we have matching polarity or matching intermolecular forces, then the energetic is balanced, right? It's going to give up dipole-dipole, but it's going to be able to make dipole-dipole. So this is the idea. Same thing with nonpolar and nonpolar, right? They can all make dispersion forces with each other. So like dissolves like. So if we dive a little deeper into this, we can sort of think about it in terms of the types of interactions that we're really balancing here. And what we want to think about is that starting out, we have these two types of interactions, right? We have solute-solute attractions. We have solvent-solvent attractions. And so this is one side of the scale. When we create the solution, right, we have solvent-solute interactions. That's the other side of the scale. So the idea is that we need to have this scale balanced, right? We need to have at least close to as strong of interactions here than what we got when we had here, right? So we're not going to lose, very much in terms of energetics and still have a solution form. So the idea is that these need to be, close to as strong or stronger than what we had to begin with. So this kind of gives you a nice reference chart here that if I'm looking at the solvent-solute interactions are greater, right? So we're actually making better interactions than what we had to begin with, then the solution will clearly form, right? This is sort of the most straightforward one. Now, if they are equal to each other, right, then the solution will form, right? It's a balance, right? Now, the last one is the tricky one. What if the interactions in the solute-solvent, the new interactions, are weaker than the ones we had? Now, the easy thing would be to say the solution will not form. But of course, it's not that simple. And so what we can say is that it may or may not form depending on how big a difference it is. Now, this is where that idea of spontaneous mixing and entropy play a role, right? So this idea of intermolecular force is sort of the easiest way to think about this. But if you have a solution that wouldn't form based truly on the intermolecular forces, it may actually form because of this idea of spontaneous mixing. So if we're looking at this idea, we have to assess that the solution will form only if the energy difference is small enough that it will be overcome by the entropy increase that we see from our spontaneous mixing. So remember, the entropy always increases, so we always have that sort of working force. The question is that entropy increase enough to make up for the difference in the energetics? And that's an idea that we're going to explore further as we get more into this material. Okay, so that brings the sort of introductory section to a close. Now, as we move into further sections, we're going to be talking about things like the energetics of mixing. We're going to be talking about how it depends on temperature, ways to express concentration, and we'll get to these topics in further lectures. So, bye for now. I'll see you in the next video.